As with the solid flow고요. 여러분들 보시는 거에는 Role of AI Machine Learning Reduced Order Modeling으로 되어 있습니다.
Okay, so this is the last talk of the day, but I guess we saved the interesting talk towards the end. Hopefully, we can spend the next 15-20 minutes and I can start showing some of the work we have been doing over the last few months in this area. As you know, probably everybody in the room knows there's a lot of interest in this field where essentially especially in the CAE community, right, whether that is CFD or even finite element analysis, electromagnetic simulations, any kind of simulation world, there is definite interest to see if we can use AI models such that these AI models can work together with CFD models. And then the idea primarily is that while CFD is great, it gives you good results. Sometimes, when you have to run, let's say, parametric studies of 100 different cases, 100 flow rates, maybe there are, design changes that you have to run. Is there a way that you can run only a few CFD simulations and then maybe use Ai Rom models to actually get the answers much quicker for the remaining parametric space, right? So, for example, that is a great area where AI can be used. So, with that, without any delay, I'll jump into the topic down here. This sort of exactly starts off with where Peter left in the previous talk here about DEM, hybrid DEM, and so on. But again, I mentioned this, but I'll take this into why and how this ties into AI Rom modeling, right? Again, as Peter was mentioning, if the weak gas-solid coupling is, on the horizontal axis goes from weak to strong, the number of particles on this vertical axis go from low to high. So, if you have basically lower number of particles and the gas-solid coupling is low, then maybe you could do DEM and DEM by DEM, I essentially meaning here, not just pure DEM, but with flow, right? Flow coupled with DEM essentially. So that's a great area. Obviously, hybrid DEM, if you can do coarse grain. So coarse grain, for those who may not be familiar, what that means is you're not tracking each and individual particle. You're going to say that if there are 100 particles which share similar properties, I'm going to group them together, and I'm going to call them one big computational particle, not in size, but as a group together, right? That's in some solvers, it's called parcels. We call them clouds, but essentially they're computational particles. So you group particles which are similar in properties, and then you can track them, right? So that actually allows for DEM to be able to solve more particles. But then, truly, when gas-solid phase coupling or liquid-solid phase coupling is really strong, that's where MPPIC, as we have seen in several examples, is quite useful. Now, why is this important for AI? Because the AI model that I'm going to build, or the ROM model that I'm going to build for these strong phase coupling problems where the gas and the solid phases are strongly coupled, so you have high volume fraction of solids or bubbles, I want the underlying physics for my CFD solver to be able to actually simulate that. Not just simulate that on simple lab scale problems or simple 2D or academic problems. I want that to be solved on a real industrial scale level, because the plan here is to build an AI or a ROM model for industrial scale models, right? So therefore, the underlying data that this ROM model is going to use also has to come from a solver which is capable of doing that. That's where MPPIC is again useful. All right, so again, just to briefly summarize, I just said some of the properties. MPPIC is important, captures the dense phase. Again, industrial scale gas solid. I want my solver to be able to resolve all the PSD given in there, because I want my AI model to also learn that. I don't want to use a two-fluid model or or a Euler model where I just have a few. I have to assume some mean size for my particles, or maybe I use DEM where I use only very fewer number of particles. I want my AI model to access that information. So that, again, MPPIC can provide you with that. Industrial scale, usually you're looking at MPPIC. And then lastly, why transient simulations, right? Again, most real-world problems, especially in gas-solid and liquid-solid, they're inherently transient. The flow is because you may, in some cases, with the two-fluid model, solve them as steady state, but that's not quite true. if you truly account for a strong coupling between the solid and the liquid there, these are transient problems, and therefore I want my AI data or AI to learn from these transient simulations essentially, right? And that's where again MPPIC comes in. It can solve, it can resolve these flow instabilities. It can actually give you information over time, as we have seen in some examples. We are solving simulations for 100 seconds, 5,000 seconds, 10,000 seconds, and even more than that. And let's say I want my AI model to run the transient phase, and then the in-between phase, and then the steady-state phase. I want to have that data over time. And that's again where MPPIC, as Barracuda, provides that for me here. All right, so very quickly, right? And then the question is, like, why does this matter? Why does acceleration matter in industrial CFD? I mean, why has acceleration always mattered in a CFD simulation, right? If you begin with initially CFD solvers, you could probably solve on a single core. We went from single core to be able to solve on multiple CPUs and thousands of CPUs. I guess the answer is that over the period of time, we've always been trying to get answers quickly in a short amount of time, whether that is accelerating, going from just parallelizing your core, being able to run on a single core to multiple cores, and now on GPUs, right? So acceleration is important. Acceleration is important because we want to evaluate multiple geometries, operating conditions, and so on. And we want to be able to do that in a quicker amount of time. Nextly, I also want to be able to optimize and calibrate my simulations. Again, I want to not just do for one case or for two cases. If possible, I want to optimize and calibrate my simulations over a huge, wide range of spaces, dimensional spaces, right? And then digital twins. Great, I have a CFD model that runs. I run it either at the beginning, planning stage of the work, or maybe I am running it to fix a problem. How about I can run simulations real time? As I have my equipment running in the field, I want to build a digital twin that actually runs real time and gives me answers real time, right? That may not be possible with many CFD models. It may take hours or days. So again, if I can find a tool with AI that can actually give me real time answers by reading in real world data, that's great. Again, that's why acceleration matters. Turnaround time, right? And then, how is the AI world shifting to help with this acceleration? AI is also shifting from, we are not just now looking at static surrogate models. We are looking at a transient, trajectory learning where they're capturing time-dependent behaviors. These models are moving away from just single condition predictions. Now the models can generalize and can go and predict over different operating conditions. By operating conditions, I mean all your inputs on your flow, particle size, and so on, and over time. And then again, I think truly if you've realized in the last, I would say probably year or two, you're seeing that many of these AI models are coming out of the academic world into real world problems now. People want to see if you can actually use them on real world geometries, large geometries, multiple, multiple parametric studies, and so on. So, and this is the key. And we at CPFD strongly believe that AI is an augmentation tool. Again, AI is not meant to replace your CFD solvers. It is meant to actually complement those CFD solvers. So, as I said, if I want to run 100 different CFD simulations, maybe I will only run 10 different CFD simulations at different points, and then the remaining 90 results will come from my AI model, which is well-trained model. So that's how we see AI augmenting going forward. Okay, obviously, again, the elephant in the room, right? There are obviously many of us are still skeptical of these AI models and ROM models, right? You'll hear a lot of debate about how good they are. Is this the next big thing? Or you read about LinkedIn posts where everybody will say that this is just a passing phase, right? So skepticism, we want to acknowledge that skepticism. It is true, right? We want whatever AI model we build, we want to make sure that it respects conservation principles as they're fundamental for our the engineering work we do. We don't want these AI models to small errors that start off that essentially will become large errors as you run longer in time or with extremely stiff problems. Out of distribution behavior, you see that most AI models interpolate well, but they extrapolate poorly. And they extrapolate poorly, that's a problem, but the bigger problem is there's no clear warning to the user. The user doesn't know what are the bounds in which the model is going to behave properly, or when is he extrapolating out of that. And then obviously validation burden, right? I want my AI models to actually not reproduce results not on just one case or two cases. I want to run them I want these AI models to work across a wide range of operating envelopes. And then deployment constraints, because large industrial workflows means large mesh compatibility. We have large meshes, it takes a lot of time. It has taken years of time for us to actually establish best practices in CFD in terms of meshing, the time steps or the numerical methods we use behind them. So I want my AI to just fit in rightly using my CFD. I don't want it to disturb my workflow. Just to train my AI model, I don't want to be running CFD simulations that are not something that I would ordinarily run on very fine meshes and stuff like that. So I want these AI models to just fit with my CFD workflow right away. I don't want to do special things or extremely special things to train these AI models. And so again, these skepticisms can be addressed by some engineering requirements, by placing some engineering requirements on my AI models. Firstly, we want to make sure that these AI models learn from behavior of validated CFD models. We want to understand, or we want to establish these guardrails where the model is working well, whereas where we see that it will fail or higher probability for failure. We want a clear validation pathway. We want to exactly understand what metrics, and these are engineering metrics like lift, pressure drop, etc. Right? These metrics are what on which we're going to validate our AI models. And then lastly, non-intrusive, as I was saying. These models should just be drop-in. We should be able to train or use these AI models on existing meshes and fields without having to mess with or change our current workflow too much. Okay, so this is a great graph. There are 4 quadrants in here. If you look at the bottom left corner, right, this is like principal orthogonal decomposition. So this is, if you remember from, this is the classic Rom model, basically, essentially built on, right? So you look at what are your principal modes of energy in your system, and then you only use 1 or 2 or 3 principal modes, and then that is a Rom model, essentially, right? It's great. It works great for simpler systems. More complex systems it doesn't scale well, and there is no physics enforcement in there. You're not binding this model by any types of physics enforcement. On the other hand, if you look at this top left-hand quadrant, I have what are called as physics-informed neural networks. Many of you might have heard about pins, essentially. The idea behind with pins is that you are actually embedding loss of conservation in your loss function. So the idea is if my loss function is just not learning from the data, but I also introduce additional loss functions which tell me that minimize the error with data, but also make sure you're respecting this conservation law. Right? That's what I mean. It's great in principle. It enforces physics. However, if you think about it, as you are updating the weights in your neural network, the automatic differentiation can get very complex, especially for large industrial scale problems. This is actually quite time consuming. In some cases, this takes more time to train than your CFD runs, right? So again, but that is prohibitively expensive for industrial models. So therefore, we believe that this is a zone in which we want to operate. We want our AI models to be primarily data-driven. The physics enforcement needs to come from the CFD solver. And again, neural operators, this is a very active area of research. There are a lot of papers you will see being published in this current field. NVIDIA has work going on in this area. But primarily what we've observed is neural operators are mostly used for single-phase flows. There's not a lot of published literature or yet established success with multi-phase flows. Okay? And therefore we believe that graph neural networks, graph-based ROM models are actually what are ideally suited for CFD or mesh-based methods, and then for industrial scale problems, which is what we have built our ROM model on here. Okay, the same thing that I've just explained, this graph-based ROM is compatible with large meshes, preserves local physics structure, has continuous time access and industrial deployment. I'm not going to go over details, but you can take a look at this. This particular model or this particular methodology satisfies these conditions or constraints we have. Okay, so I'm going to take a moment here to explain this slide because this is where actually all the sort of information about our ROM model is given. The name itself, firstly, the GNN stands for Graph Neural Network ROM model. The name Continuous Time Graph Operator. Each one of these terms has a meaning to it. Let's first understand the meaning of this graph, right? What does this graph imply? So what I'm showing on this picture here is a 2D cross-section of your CFD grid. You have some sort of a variable here, field variable here, that could be pressure, that could be velocity, that could be mole fraction essentially. So the first important thing in CFD, as we were learning, we understand about gridding, right? The importance of breaking down my domain into this grid, which are essentially smaller control volumes, right? And you learn about this mass balance, so between one control volume to other control volumes. Essentially, even though you're breaking your entire domain into smaller chunks, you are making sure, or the understanding is that each one of these cells passes information to the other cell, whether it's in one direction, it's multiple directions, depending on diffusion, advection, and so on. But the information is transmitting from one cell to another cell through the phase interface, right? So there's a lot of spatial connectivity. So you see this solver as you're solving, if there is something happening at the bottom of the reactor, this information through the the grid connectivity is transferred to the top of the reactor, right? This is the idea of the CFD mesh. You're actually, that's how you're enforcing mass or momentum or energy conservation. So when you are trying to build a ROM model, which you want that ROM model to replicate this spatial connectivity. And that's where this graph part comes in. So each one of these nodes you're seeing is actually the CD center, the control volume center for your CFD mesh. And you see these edges that connect information between two nodes. Those are your faces between two cells. That's your face between two cells. So just like a CFD mesh is aware of the neighboring cells, a graph is exactly built on to replicate the structure of your CFD grid. Each one of these nodes is actually talking locally to the other nodes. In this case, we use 4 layers or 4 stencil width. If you remember your finite difference methodology, you're talking about stencil widths, one stencil, 2 stencil. We're talking about 4 stencil widths, which is what we put the number here. But that's how exactly the message passing interface is happening in this graph. So the graph is meant to capture that spatial connectivity from your CFD. Now this is the second important point here. We are actually, so when we are training our model, we're obviously giving it all the spatial locations that is embedded in the graph. And then we are passing on all the field variables, right? From the CFD, it is reading the cell centroid locations, the phase locations, then it is reading all values in those cells, whether it's pressure, volume fraction, weather velocity, everything. But then all of this is read at a single point in time, right? All of this information is at one point in time. However, we do not want to pass this time as a discrete variable. What we find is that, in fact, if we convert this time into the Fourier space, so if you essentially convert your time into a series of sines and cosine functions, and if you remember the advantage of sines and cosine functions, right? I think we use 8 pairs of sines and cosines, and then we use logarithmic spacing between them. The key idea is you're moving away from a discrete point to a range of frequencies, rich frequencies, where information is much more, the time variable is much more widely spread for the ROM model to learn from. Right? Again, this is an input that goes into this. The advantage with also using Fourier series is these are continuous functions in time. Therefore, whenever my ROM model learns from this information, it can then give me information between those time points, because now this information is being spread as continuous functions, right? So that's where the continuous time comes from. So time is not passed as a discrete function, time is actually passed as a continuous time, Fourier space. So with this combination, essentially, continuous time graph, and then comes your operator learning. Now this operator learning, people might be familiar with operator learning. The idea is that the neural networks are essentially learning the entire snapshot of your CFD field as an operator learning, right? So it's at any given instant of time, it is learning everything. That entire multidimensional space of CFD is being learned, and this is the brains of the ROM model. And here is where a couple of things. I think one thing I should mention, I think it's 128 hidden layers per node. That is how dense these layers are per node to learn. And once that is done, then this is where the ROM model is actually able to infer and give you that space. So this continuous time graph operator, actually what it does is now it allows us to infer information as a single snapshot in time. If I want information at about 3.7 seconds, I'm going to directly infer that result based on this methodology. I don't have to interpolate or extrapolate at that particular time. All right, with that, let me look at brief results here. Same hydraulic fracturing application I was showing. In this case, I only have one single fracture. So I have 3 inlets, flow comes in, 3 inlets, flow goes out. The geometry is about 4 meters long, 0.3 meters tall, and about 0.01 meters thickness. Again, we talked about this fluid, it's not Newtonian, there is some solids in there. The key is this, we are using about 170,000 cells in Barracuda, 9 million Lagrangian parcels. Again, this is 9 million cells for a problem which is 4 meters in length. And that's only possible through a methodology like MPPEG, right? We have modified a drag model to account for non-Newtonian drag here. And then, okay, so if you see the training envelope for the ROM model is these 4 velocities, 1.2, 1.3, 1.5, 1.6. So we train the ROM on these velocities, and we want to test the ROM on this unseen velocity, which is 1.4 meters per second. So if I move to the next slide, I'm showing you, this is the volume fraction of particles. So the particles are coming from the left, and they're settling down with gravity, and the height of the particle bed is increasing. This is my CFD, and this is my ROM model prediction below here. And actually, I just don't have to look at qualitative results. I can then quantify them. The solid lines are CFD, and the dotted lines are from the ROM model. If you see that the mean average bed height error is less than 0.02 meters in this case. This is for a fluid solid flow condition. All right, how about gas solid flow? If people who are looked at our training material might be very familiar with this gasifier example. This is one of the main training example we use to train our users. So this is a cold gasifying unit down there. Again, the key is there are some conditions. Obviously, I don't have to explain you what a gasifier is. But if you look at the grid information here, again, we're using 80,000 grid volumes, 1.1 million Lagrangian cells. The key difference from the previous simulation is there's also chemistry involved in this. There is devolatilization, char, oxidation, steam gasification. Now, this flow also includes reactions in it. And again, where training envelope is these flow rates, and we are going to test the ROM on an unseen condition of 0.85 kilograms, right? That is a flow rate at which the ROM hasn't been trained on. All right, let's look at some static images down there. Firstly, I'm looking at particle, these are CFD results, these are ROM results from the graph neural network ROM. Particle volume fraction at time average, right? These are time average results. So you can see that again, qualitatively, there's a very good match. Methane composition, CO2 composition. You can actually look at the root mean square error essentially in each one of these results here between the particle volume fraction, the methane and CO2. Then you can also do some correlation essentially. So not just look at mean values, but if I were to correlate one-on-one, cell to cell, how does the correlation look like? Greater than 99% correlation coefficient there. All right, not just time average, how do the transient results compare? CFD and ROM, same, volume fraction, methane, CO2. Again, you can see that even the transient simulation results are actually comparing very well between the ROM and the CFD. Right? Again, we can do this correlation coefficients over time, and you see that the greatest error actually is in the starter phase. But again, good correlation comparison, right? And again, fair enough, even if there is a tiny error here, what is the key advantage here? I'm going to let this go in a second, but you can see that even over transient time, the results actually compare very well between those two models. How does this actually mean in terms of timing? That which is what the key point I was mentioning at the beginning, right? So for the hydraulic fracture case, liquid solid, the full CFD takes 68 hours. Whereas to train the raw model, it takes about 1.7 hours. The inference phase is about 0.8. But once it's trained and everything is done, it takes about 10 seconds to get the answer back of that trained raw model. Similarly, from the fluidized bed gasifier, right? The training times are smaller than this. But again, you can get answer within seconds here. Not only that, this can also be green because once, obviously, you spend a lot of energy running these CFD models, training them, but once they're trained and run, the energy consumption to run these models is actually quite low. All right, with that, very quickly, I'm going to quickly walk through the slides. All I'm trying to say is I established some foundation requirements for how my ROM, so for how my industrial CFD ROM should look like. or is, I said that industrial safety ROM has high fidelity transient trajectories, it has strong multi-phase coupling, and therefore I want this ROM model that is built on, I want that ROM model to have access to this data to be able to actually give me good answer or give me good answers for such industrial scale problems, right? So again, this is self-readable. If you look to the slide, you will understand this actually ties back to what we started off with. With that, I am actually going to leave this slide here. Again, I want to acknowledge this work is done by our staff senior engineer, Dr. Saurav Mitra. So again, if you want a demo for a ROM tool, please reach out to us. Please reach out to me or to Peter, and we can actually arrange a demo for this for you. With that, I'll run on time here, so I'll take any questions you have.
I just got a question about training. So, who gonna train the model? The user or directly from the company CBD software?
So I'll answer this first, Peter. Maybe you can say more on that. But okay. So this ROM tool that we have built right now, basically here, the idea is that we will eventually, it's not quite ready yet. For now, we are using this in projects, or we plan to use this in project that comes across to us. So if our customers come to us, they want to build ROM models, we will build them for that. But later on, towards the end of the year, we want to release this as a product, where the users can license this product from us, and then they can actually use this ROM model to train based on their own simulations, and then use them. Now, if training is prohibitively expensive for you, you cannot do that. Then again, we can work on a project model with you where you give your data, we train it, and we can show results. So there are multiple ways which we can do this. But yeah, that's the plan.
So it means basically for the simple application, probably it can provide by CPD software, but for very specific application, it's going to be like a collaboration with the customer, right?
So when, if I get your question right, you're saying that is the ROM model only capable of solving simple problems, or is the collaboration only possible with simple problems right now? What are you asking?
I mean, the one.
Because the physics here is not simple, right? The graph we looked at, so yeah.
GNN ROM.
Okay, so you're saying the collaboration part of it, right? Okay. So again, if you don't have the capability to build this ROM model, you can license this from us, and then we will help you actually train that ROM model as a part of a project agreement. But let's say you have your own ROM models that you already invested time, you're building it, or maybe you're using the physics Nemo library, for example, from NVIDIA, where you build your ROM models using that library. Then obviously use that ROM model, but then the key idea is we will release some features later in the year where we will provide, because you need data, all these models are data hungry. That synthetic data is coming from Barracuda, that's the key. Our key metric here is the ROM is an add-on tool on top of Barracuda. The synthetic data has to come from Barracuda for these type of problems, right? But we will make certain features available where you can export information from Barracuda that can be compatible to use your own ROM models with. Thank you.
Actually, I have one question. I want to get your opinion about extrapolated data. But your case is only intrapolated data. So
that's right. I speak how much I know. Obviously, Saurav knows more about this because he's the one who's built it. You're right, though, that I think for now the plan or the way it is meant to do interpolation. It's not meant to do extrapolation beyond range. Now, we are doing some active work in that field where we are collaborating with NVIDIA on using some of their physics Nemo libraries to look at examples where, if you remember, I showed you an application where that property transport, where I showed you 3 fractures 5 meter, 10 meter, 20 meter spacing. You know, so the raw model is, let's say, trained on 5 meter spacing, 10 meter spacing, 20 meter spacing. But I want my raw model to predict what happens at 15 meter spacing. It was never trained on. That is extrapolation because that geometry never existed, right? That geometry never existed. It never got trained on. So that is something that we're doing active work at. We are looking at that actively. Again, this is a very fast moving field, very fast developing work. If you talk to us in a couple of months, we'll have made some more advancements on that. So if you are more interested in this, please stay in touch and talk to us, and we can let you know where we're going with that. But for now, this capability would be mostly within the training and interpolation environment. But then again, even though it's interpolation, remember it is looking at times which are unseen as well. It's a single snapshot interference. I don't have to run my model from time t equal to 0 to 100 seconds. That's the biggest advantage. So it's very quick in terms of getting back to results. All right.
I have one question more about this application. This result is 3D or 2D surface result?
These are all 3D surface results, yeah?
I want to. Yes. This result is surface result or cell result?
So I mean, I don't know what they're plotting. If you see, in fact, they're plotting on the inside. It's probably all surface plots you're looking at, but the data has been trained to replicate 3D data. Everything is 3D. When we calculate all these numerical values, it is on 3D data. Plots may be just showing you on surface plots there.
Thank you.
Yeah.
You said this will be available at the end of this year. So does it include extrapolation also?
That I am not quite sure yet. Yeah. Again, like I said, this is such an active field. I will continue to work on that actively. So for now, again, like I said, we want to look at cases, very edge cases. We're actually talking about very, very cutting edge work. Some of the technology or some of the underlying architecture we're using for NVIDIA, those papers are just getting published in the last couple of months or so on. So we're doing very, very cutting edge work down there. So honestly, I think, it will take us a few more months for that to mature and to give you more better answers on that. So. But that's exactly how everybody's trying to do that. There's a lot of research I can tell you going on that, and there's a lot of success as well that's being seen in that. So it's not out of realms impossible to do something. But again, we're talking about multi-phase flow systems here. You will see many literature in single phase, like aerospace and so on. You might see a lot of papers and work.
Thank you very much for a very nice talk. So I have a very quick question.
Yeah.
So actually I am not familiar with the term about the ROM. So as far as I understood, the term is that for example, if we would like to simulate the 3D model, then we have to enter temperature, flow rates, some other things, blah 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 into there. However, when I use the ROM, then the only thing that we use is just the time. So that means the input parameters getting down. So is that the definition of the ROM?
No, actually. So the ROM stands for reduced order model, right? So it is still a CFD model, but all we're saying is if I want to run this at 1.8 kilograms per second, the CFD model, I have to probably I've run this at 1.4 kilograms, 1.6. I want to run it at 1.8. I will start running the simulation at that point, right? I will run it for 200 seconds. I will get my results. It's the same like running my raw model as well. I will still input that 1.8 kilograms as an input, except that the ROM has been already trained over a whole range of those conditions, right? Such that, like I said, if the ROM is trained on, if the ROM has been trained on, let me go back here, yeah. The ROM has been trained on this, and this flow rate. Now, but there are many flow rates in between that I want to know an answer for. Then I don't have to run in my CFD model. I can just use my ROM to give my answer. And that answer only takes about 10 or 20 seconds to get back, rather than that full 2-3 hours to run the CFD simulation. Does it make sense? Right? As a simple example. So you're not just inputting time, you're actually inputting any conditions, like input conditions that you would enter into your CFD model, into your ROM. All those conditions will be entered like that, except that the results will come back to you much quicker.
Okay, then that means in this case the flow rate is the input parameter, right?
Yes.
The kilogram per second is the input parameter.
Uh-huh.
But in that case, the other parameters should be the same except for this kilogram per second, right?
So not necessarily. What other parameters like? So the pressure and so on. You mean, for example?
I mean when you take a look at this table, upper table, a lot of the parameters are in there.
Yeah.
So the training parameter is the kilogram per second.
Yeah.
That means the only thing we can change is kilogram per second.
Not really. You can change air composition as well. You can change this gas composition.
Oh,
Exactly.
okay.
Yeah.
Okay.
Yeah. The ROM has learned that relation between your inputs to outputs. But these are something. These are okay. So there are certain parameters, because what is the most significant parameter out of which it's going to affect? It's your flow rate, right? So that is something that you will include. But then this gas composition behavior, that you don't have to keep the same thing. You can input it in a new way. We can chat more about this. Like I said, my colleague Saurav can probably even answer better than this on how well to infer and use this model. But these are all great questions, exactly, right? So, but yeah, as far as I know, you don't have to use the same values.
And maybe just to clarify, if we're changing gas composition there, we would be extrapolating because we've not trained the ROM on different gas compositions in this case.
This is just the input value though, right? Inside the reactor, the gas composition is probably varying from 0 to 100% anyway,
I see.
right? So
Yeah.
the ROM has learned on that, yeah.
But in general, we're showing a single variable to change in training and in
Getting back the result of it,
practical,
yes.
but really, in reality, this is going to be multivariable. You could change.
That's right, yeah, the gas composition, the ROM, because internally the gas composition goes from 0 to 100%.
That's right.
So the ROM will be able to predict that back for you. Yeah.
Okay, thank you.
I have a quick question about this, the way we're using this AI method. So, in my experience, the particle position or velocity is just obtained by few calculations. So we don't need to do some AI training or the kind of more time-consuming method to predict. But for this, the velocity and the speed or energy, we need to do the iteration method, which takes some time. So how do you use this your AI? So you train all of this field at once, or you can do some separate training?
So we are providing it snapshots in time. It is taking in both Lagrangian data. So at a given instant of time, it knows where all the particle positions are. So it trains on that. It also knows at any given time all the cell values for gases and whatnot, right? It is basically you're providing a series of snapshots in time to train the model, going from 0 seconds to, let's say you run the simulation of 100 seconds. You're providing you're saving files at, let's say, every 1 second, 2 seconds, 3 seconds. All of that is going into training to learn. So that's why the ROM is able to predict over any of that time range for you.
Yeah, what I meant is, if you have this velocity and species or energy field, you can directly get this particle position from this.
Yes,
Or-
but no, we actually learn directly that from the CFD. We are not doing any special calculation, like you said, because we know the energy, because I know the pressure difference in the cell. I'm not then asking the ROM to predict how the particle should move. No, I am directly learning everything from the CFD, because the CFD is conserving all the quantities that need to be conserved, right? Whether the ROM doesn't have any built-in constraints for conservation in it. So it's all truly data-driven. So that's why it comes from the CFD. That part does come from CFD.
And I would just clarify, when we talk about ROMs, there's really two different things we're talking about here. So Shashank has presented our own research, which happens to use the graphical approach. This is what we're doing, and it's the latest and greatest in R&D and process. So we always hesitate to present something that's not a product yet, but we gave the first public presentation earlier this month in Houston, and the timing worked out that we're also showing it here. So this is what we are doing. But Barracuda is not tied just to our own ROM. So I know many companies here probably have AI initiatives, and any AI, any ROM or other type of AI needs data to train it. And whether that's physical data, synthetic data from simulation data, a lot of that data comes from various sources. And Barracuda can be used with other AI and ROM tools. They don't have to be ours. So just keep in mind, this is what we're doing. There can be other approaches, and Barracuda might couple with that very